All right, so let's begin our review of magnetism now. So, big thing, magnetic fields are created by magnetic dipoles, or at least like permanent magnets. That's what we start with. Monopoles do not exist, and they are vectors. Just like electric fields, they are vectors. Objects with their own magnetic dipoles will orient in the direction of the magnetic field. That's generally how magnets work. So if you have a magnet as a north and a south end, the magnetic fields go like this. They point from positive to negative. They go in this direction. Go from that positive. And technically, the reason they have a magnetic field is because they have there's a little dipole in here, and so that continues the magnetic field. All right, magnetic fields flow from north to south, and they form a closed loop. There's a magnetic field. Actually, we usually draw it outside of the bar of the magnet, but it technically is forming a loop here. All the magnetic fields have to go in a loop like this, okay? And it's primarily, the math's pretty involved, but it's because there's no monopoles. They always exist as a dipole. And so that forces the magnetic field to be in a loop. Unlike electric fields, which can just kind of go in a straight line forever. Magnetic fields do have to form a loop eventually. In terms of magnetism, some properties, which is, I think, a little bit new to AP Physics C to focus on, is there's the difference between ferromagnetic materials versus paramagnetic materials. And this is just a terminology thing that I want you guys to know, is that ferromagnetic materials can be permanently magnetized. They have a strong response to magnetic fields. Okay? And that's how they can be easily made into permanent magnets because of this, because they have a strong response. Paramagnetic are pretty weak. They have a little bit, but they don't really respond to magnetic fields. And that is one of the things, is if you remove a magnetic field from a paramagnetic material, it's going to lose its magnetism. So these are examples of very weakly magnetic materials, or paramagnetic materials. And then some more definitional stuff. Magnetic permeability is the amount of magnetization due to a magnetic field. This is not tested heavily, I don't think, in any of the examples, but if you ever have like a transformer with a core, then this is like an important property of that. But it's in the course and exam description. I never really seen a question on it, but it's based on temperature, orientation, strength of the magnetic field. But anyway, like this is a big part for transformers when we are doing some power conversion utilities or engines and things like that. Okay, but let's move on to the actual stuff you're going to be tested on. First thing is magnetism and moving charges. That is, there's two things that happens. Whenever you have a charged particle moving through a magnetic field, it experiences a force. This is a huge principle. Okay, and this is not an intuitive principle, but if a charge moves through a magnetic field, it will experience a force. And there's two ways that happens. Charges can move as a current. So you have this force equation, or I tend to use this equation the most. If you have a single charged particle moving at a velocity in the direction, or perpendicular to some component perpendicular to a magnetic field, you will experience this magnetic force here. Use the right hand rule. Remember, the right hand rule is your three fingers, and it's like thumb, then index finger, then middle finger, and you always make your right hand as like a corner like this. This is always going to be the leftmost of the. If you write the equation in that form, it's going to be force, velocity, magnetic field in that order. 1, 2, 3, right? Use the right-hand rule to identify direction of the force. Remember, if Q is negative, then you kind of just flip it around. Some people switch to the left-hand rule. I just say, whatever you get as your answer, flip it in the opposite direction. Okay, in a uniform magnetic field, a charged particle will move in a circle because this force is perpendicular to the velocity. It acts as a centripetal force, right? Because it causes centripetal acceleration. Because remember, centripetal acceleration is perpendicular to the velocity. So in that case, it will move in a circle if it's a uniform. That's because the force vector will always be perpendicular, and then it will move in a circle. The other thing is moving charges or current also create magnetic fields. So not only does a moving charge experience a force from a magnetic field, it can also create a magnetic field, right? So any current will generate a magnetic field as well. So it can experience a force when exposed to a magnetic field from some other thing that's causing it. Could be a magnet, could be other currents moving, or it can also create its own magnetic field. Okay, for a long wire, the magnetic field moves in a circle around the wire, and that's due to symmetry. So if I have a very long wire, okay, there's no reason to think it should be longer on one side because I have rotational symmetry. If I rotate it, it should look the same, which means like it has like circles, concentric circles that as the magnetic field, because remember, magnetic fields have to be those closed loops. All right. Now, how do we actually compute the magnetic field from a moving current? So if you have a current in a piece of wire and you want to generate the magnetic field, at its core, we use Biot-Savart Law. Okay, so it will it's a very cumbersome equation to use, but you want to make sure you understand how this works. It's a differential. It's set up as a differential. You obviously have to integrate it to get the total current around the loop from the entire loop. But the way you want to think about it is if you have a segment of wire with a current here, so this is a segment, the length is dl, and the dl vector points in this direction, so the dl vector points like that. And I care about the magnetic field. I want to know what the magnetic field, the contribution of the magnetic field here is. Then what you do is you do dl, and your r hat is a unit vector that points from here to where you're interested. So it's an r hat vector. R hat vector is a length 1 vector. Okay, length equals 1. Just as a reminder, it's a length 1 vector. And you would cross these two vectors. Now, obviously, we just want to get the direction. By cross product, we're going to use our right-hand rule to get the direction of it, right? Because this is going to be our index finger. This is going to be our middle finger. And then where my thumb points is going to be the direction of that vector. So then you want the component. You want to know which direction that is. You want to take that component, and when you integrate it, remember you got to integrate just the component in that direction, in the z, x, or y, or whatever direction it happens to be in. R is the actual distance from that point. So this distance here is this distance here is actually r. R hat is unit length though, so keep in mind that when you do the cross product, you do need to just make sure. Now, in AP Physics C, you're mostly going to have very, very, very simple ones. That is loops and calculating the magnetic field here, or maybe a loop of wire and it's off axis. You're not going to have to do anything super complicated, but you may have a loop of wire like this. These are the kind of two common examples that you'll be testing on what you need to know to apply this law. Something easy where the dl vector is somewhat perpendicular or at least symmetric, and so that this integral ends up being really simple to set up. But you do need to know how to set them up. What your goal is to take any of these loops, split it into little segments, find the dl, find the r hat, and then find the contribution and the direction, and then decompose. And I think we'll go through some examples in at the end. Okay, so Ampere, so Biot-Savart is very cumbersome to use. So we have another technique, Ampere's law, which is a little bit like Gauss's law. If you remember Gauss's law, you could have found electric fields by just integrating the dq over r squared for all the charge distribution and adding them up. Very tedious, just like Biot-Savart is very tedious. Gauss's law comes in and says like, hey, there's an easier way to compute this integral, right? This thing, and there's or a technique. And so Ampere's law kind of falls into that. It's a powerful way to use it. And like Gauss's law, it requires us to use symmetry and know and to take advantage of symmetry. You have to know how the magnetic fields are oriented, and then you can use a nice trick. So the way this equation works is the left side of the equation is a line integral. It's called a line integral, and when you take if you take multivariable calculus, you'll learn it. But it's essentially dot product between the magnetic field and the loop. So you have to create a loop called an Amperean loop. Kind of like in Gauss's law, you have to make a Gaussian surface. In Ampere's law, you have to make an Amperean loop. And that loop most likely needs to be, okay, so there's some rules. We'll talk about the Amperean loop. But you're going to do this integral, the Amperean loop. Now again, just like Gauss's law, even though it's an integral, a flux integral, in general, you're picking an Amperean loop so that integral is very simple to do. Just like in Gauss's law, you don't actually do much of an integral. When you do this integral here, you're picking a surface where this integral is very simple to do. Okay, so you don't actually integrate anything. Similar thing here. And then it's equal to mu naught I. I is, it will be written as enclosed, but I tend to think of it as it pierces the surface. That means the Amperean loop creates a surface, and the I pierces is how much current is going to actually go through that surface. Okay? That's the part that goes here. So it's like you're making a loop. Okay, it's a closed loop. It's not a closed surface like Gauss's law. Gauss's law was a closed surface. This is a closed loop, and then that creates like a little surface, and then we're trying to figure out how much current is piercing through that loop there. Okay? So, tips for choosing Ampere and loop. You want to identify the symmetry of the situation and the direction of the magnetic fields. Ideally, it's going to be circles or straight lines. You want to pick a direction where the loop is either completely parallel, okay, to the magnetic field, or perpendicular. Because if it's perpendicular, the dot product will be 0, and if it's parallel, you can just multiply the magnetic field times the length. Okay, so you either want to do that. That's why it's important that you know the direction and the shape of the magnetic field when you're doing the Ampere and loop. Okay, you can use this for a long wire. Let me just show you the quick derivation for a long wire. If you have current going through here and it's creating a magnetic field, and we know that it creates a magnetic field with a circular loop, like we know that's the direction of it, okay, right? And we use our right hand rule. Thumb points in the direction of the current. Our fingers curl in the direction of the magnetic field. So we know it goes like this, but how do we figure out the amount of it? Is we say like, okay, well, by symmetry, everywhere along this circular path is going to have the same strength magnetic field, because there's no reason to think over here should be stronger than here, because if I rotate it, if I spin the wire, then this part's going to be down here and this part's going to be here, but still the same wire with the same current, even though I just rotated it. So this point and this point, or anywhere, no matter how much I rotate it, has to have the same strength. So my Ampere and loop's going to be that circle. So when I do this integral, it's just going to be the magnetic field times the length of the loop, which is 2 pi r, where r is this distance here. And that's equal to mu naught times the charge enclosed, or the current that goes through here. And as you can see, this current is piercing through this circle, going through this loop. So the magnetic field is mu naught I over 2 pi r. So you need to understand that derivation. That's where that comes from, magnetic field from long wire. It's also used for a solenoid, and we'll go through an example later where we go through deriving that for a solenoid. But you can do the same thing for a solenoid, again, knowing the direction of the magnetic field and how to set up the Ampere and loop. Magnetic fields can also be created by changing electric fields. You only have to know this qualitatively. When I was reading the course and exam description, you don't need to know this. I've never seen a question testing on this. This is a more advanced concept, but basically if the electric field is changing, you also can create a magnetic field, but you do not need to know any analytical stuff with that, or you have to compute anything. You just need to know that qualitatively, that if the electric field varies, it also causes a change. The electric field varies, you can argue, by currents moving, kind of. That's not the only way it can change. But when the current changes, then that, well, because of a current is changing, it can cause charges to move and change electric fields. That current can create a magnetic field. Okay. All right, so let's go through some examples now, because I think that's what you're really here for, to really understand how everything works. Okay, 3 long wires, R, S, and T are arranged in the XY plane, parallel to each other. Which of the following correctly indicates the magnitude and direction of the magnetic field at the origin of the coordinate system? So here we're going to use the long wire that we just derived. B is equal to mu naught I over 2 pi r. All right, and we want to use Ampere's law. We showed how Ampere's law can be used to prove that. So in this case, we have a point here, and we got to think about our right-hand rule for the direction. So thumb goes in the direction of the current. Our fingers curl in the direction of the magnetic field around it. So wire T, S, and R are each going to create a magnetic field. So for wire T, my thumb is pointing to the left. My fingers will curl around it up into the page, down this way, out of the page. Okay, so that would be the direction of the magnetic field for this guy. So he's going to be going into the page there. That's the magnetic field from wire T. How about wire S? Well, his current's going to the right. So my thumb's to the right. My fingers will curl up and over in front, and then behind it and back. So it's going to go like this into the page, coming out, and then out of the page like that. Okay? So that is the magnetic field from S. So they're both going into the page. That's really important. And then wire 4I, and then for R, his going to the right, also going into the page here, and then coming out of the page there. So all of them are going into the page, which means they're all pointing in the same direction, and so we can just add them straight up. So if I want to do this, we're just going to add them up because they're all pointing in the same direction. So this one is mu naught, and the current is 2I divided by what is that distance there is going to be d. And then Bs is the magnetic field from S is going to be mu naught 2I. And what's the distance from this wire to this point is, let's see, this is minus d. That's at the origin. Oh, it's 2d. So it's 2d away. And then this one is mu naught 4I over the distance here is 4d, right? So, and then it's going into the page, and what are they saying? Which way? Oh, positive z. I'm hiding it. Positive z is out of the page. So this is going to be in the negative z direction, because we said it was going into the page. And so this is going to be 2 mu naught I over d. This is going to cancel. This is going to cancel. So you have one of these, two of these, and then two of these. So it's 4 mu naught I over, oops, I'm sorry, so 2 pi. This is 2 pi. I forgot the 2 pi's here. Over 2 pi times d. And that's going to be 2 mu naught I over pi d in the negative z direction. So it's going to be c here. So let me just check I make that right. So it's mu naught I, one of those, two of those. They're all 2 pi d on the bottom. So it's going to be 1, 2, 3, 4, 4. Yeah, okay, I think that's good. I think I did the math right that time. Okay. Let's take a look at this one. So we have a semicircular loop with a clockwise current is placed in a uniform magnetic field that's directed into the page. F1 is the net force in segment 1, which is a straight portion of the loop. F2 is the net force on segment 2, which is current important, which if found correctly indicates the relative magnitudes of F1 and F2. Okay, so we have a current through a magnetic field. So we got to think about force. There's a force caused by a magnetic field, and that's going to be QV cross B for a point charge particle, or because we have a segment of wire, it's going to be IL cross B when we do this, right? Or you might break it into chunks. So let's think about segment 1. So segment 1, he's going to have a current going to the left, so my index finger points to the left. My magnetic field is into the page, so I got to rotate it. Keeping my finger to the left, I'm going to rotate my finger away from me into the page, and so my thumb is pointing down. So this guy is going to have a downward force, okay? Now we have this part here, which is a little bit tricky because the IL cross B, it kind of is going to vary if you think about the contributions, right? So like the currents, we got to break it into segment, almost like Biot-Savart. We're just going to break it up into segments, but then just think about the right-hand rule. So our finger's going up into the page. There's then a upward to the left component, upward to the right, upward. It's going to have these components that are perpendicular to these segments. Upward, right? Based on our right-hand rule. Okay. Now, the math is a little bit tricky, but there's no reason, but basically the net forces of this is going to point upward. Okay, so there's going to be an upward component here. So now we have to think about the direction of F1 and F2, relative magnitudes of them. So let's first get the directions, right? F1, so F1 is on the bottom segment. So this is F1. F1's pointing down, and F2 is pointing up, right? So F1 toward the bottom. Okay, so it's not C or D. F1 is toward the top of the figure, right? Okay, so not C or D. Definitely one of these. Is one of them bigger or not? Now, this is one of those things that is like probably easier to think about a little bit physically. Like if we put this loop in a magnetic field, like on Earth right now, do we think that it's going to experience a net force? Like, do we think this thing is going to accelerate? And the answer is no, right? Like otherwise I would have a really cool way of accelerating things all the time. Like I would just put a loop in and put a magnet over it and it would just like slide. Like that would be super cool, but that's not really going to happen. They're actually going to cancel each other out. The math is probably not easy to necessarily show you that it will do that, but yes, the net force is ultimately going to be 0 on this loop. It's not like it's just going to create a net force on it. Even though there's a current moving through it. So they're actually going to be equal to each other. Okay, let's go through a couple FRQs here. The figure above represents different views of two long straight wires carrying currents, I1 and I2 respectively. Point P is a horizontal distance away here. Derive an expression for the magnitude of the magnetic field at point P due to wire 1. So wire 1 is creating a magnetic field, and they're circular loops, and my thumb is pointing towards me. That's the direction of the current, and so it's going to curl in the counterclockwise direction. So the magnetic field is going to go like this. It's going to have an upward component right there. Right? So right there is the upward component from 1, and that's mu naught I over 2 pi r. Right? We proved with Ampere's law. So it's just going to be mu naught times I1 over 2 pi times whatever that distance here is, d. That's mu naught I, because I1 is just I, over 2 pi d here. Okay, so that is due to wire 1. Now we want the net magnetic field at point B. So wire 2 also creating a magnetic field. And if you think about this guy, my thumb's pointing to the left, it's going to create a circle. And in front of this wire, it's going upwards. So it should be upwards here, then into the page, then around here, and then out of the page, right? So that should be, and on the back side of the wire, it's going down on the other side because my thumb is pointing to the left, right? So from my perspective. Okay, so then that's going to be the magnetic field from wire 2. That's going to be mu naught. His current is 2I, okay, over 2 pi times the distance from there to there, which is also d. So that's mu naught I over pi d. Now, they're pointing perpendicular. I have a component upward and a component into the page. And if I want and I'm going to rotate it, and if I want the magnitude, we just use Pythagorean theorem. So this is going to be the square root of b1 squared plus b2 squared because they're perpendicular to each other. So that's going to be mu naught I over 2 pi d squared plus mu naught I over pi d squared, like that, right? And so then you can pull out a mu naught I over pi, and then you can pull out a d as well. And so then you're left out, there's a square of them, and then you're left with just the 2, or 1/4, plus, and then here you're just left with 1. So it's going to be mu naught I over pi d times square root of 5/4, which you could write as square root of 5 over 2 if you wanted to. Okay. Wire 1 is now released, which the following describes the initial motion of wire 1 due to the magnetic field of wire 2. Assume gravitational effects are negligible. So we have a force, right? Because why? Because there's a magnetic field. There's a magnetic field from wire 2 onto wire 1, and wire 1's carrying current. So wire 1 has current going through a magnetic field, right? So let's take a look at it. And they're going to be equal and opposite. So 1 is going to act on 2, and 2 is going to act on 1 like an equal distance. So let's draw the magnetic field from wire 1 that's on wire 2. So if we look at this guy, he's going to have a magnetic field, like as it approaches this point, he's going to have a magnetic field that's kind of like this, right? Like this. Let's just talk about this one. It's going to have multiple magnetic fields. So it's going to have there's multiple concentric circles like this. Okay, so what we're having is a magnetic field, and the directions are like this. It's counterclockwise because the thumb's pointing at me, and my fingers curl counterclockwise around my thumb like that. Okay, so we have a current, but look at, okay, so one thing to notice is if you look at the segment right here, right, the magnetic field is parallel to the wire, right? And remember, the force on the magnetic field is the IL cross B. That means the current, there needs to be a perpendicular component, because if the cross product is, if the two vectors are parallel, then the cross product's 0, right? So there's no contribution of force from this component. There's contribution of the parts that are going at an angle here, like this and this, right? So there we have some magnetic field going this way and this way, and so there is some contribution. However, they're going to cancel each other out, like by symmetry. It's like we decompose the magnetic field into be like one like this and one like this, right? And so we only care about, actually, let me think about that. We care about, sorry, I'm decomposing it incorrectly. Sorry, it's pointing down into the right here, so we got to make it right and down. So there's a downward component perpendicular to the current and an upward component perpendicular to current. They're going to exert forces, but those are going to cancel each other out individually. So no matter where we are symmetrically, like every time we hit that wire, they're going to cancel each other out because of the direction of the magnetic field. The component that we care about is always going to, on the right side, it's going to have an upward component of the magnetic field. On the left side, it's going to have a downward component of the magnetic field. But by symmetry, it's going to be the same, and they're going to just eventually cancel each other out in terms of the force component, right? And so end up, the Wire 1 will not move because the net magnetic force will be 0. And you can explain that again by saying, you know, components perpendicular to the current will cancel each other out, will create forces that cancel each other out. Okay. All right. So that's that one. Okay, let's look at a solenoid. So a solenoid is used to generate a magnetic field. Solenoid has an inner radius of A, length L, N total turns of wire. Power supply is connected to the solenoid, generates a current I as shown in the figure. The x-axis runs in the axis of the solenoid. Point P is in the middle of the solenoid, and L is much bigger than A here. We want a direction of the magnetic field at point P. So this is a bit of a right-hand rule. You got to think of it as like there are several currents that are happening, right? So there's loops. There's these loops of currents, and you could use Biot-Savart to find the magnetic field, but we're going to show how we use Ampere's law. But for the direction, just imagine that when you're looking at it, let's see, it generates a current. And so if you look at it from this direction, it looks like it's going clockwise. If you were looking, if your eye were over here, let's put some eyelashes so you can know if I'm looking in this direction, then the loop will look like this. It will look like the current is going clockwise. Okay, hopefully you can see that based on the picture. It's going clockwise. So I put my thumb in the direction of the current. If it's on the left side, my fingers would curl into the page. Down here, my fingers still curl into the page. And when it's going up on this side, curling into the page. So the magnetic field is pointing, all the components are pointing into the page, which in this case would be pointing from the perspective of this way would be to the right. Okay, so into the page when I'm looking at it, you know, if I were to take the solenoid, like the solenoid's like this, if I look this way, it's like, oh, it's going into the page, which is towards my right when I come from the side. So it's going to be pointing to the right here like this. So that would be the positive x direction. See the arrows here, x, y? That's the positive x direction. And I'm not going to write out the words. I just explained it to you. You can write out the words with right-hand rule. So just explain that by the right-hand rule, your fingers would curl to the right from all those components from a loop. Okay. On the cutaway, draw an Ampere loop that can be used to determine the magnetic field. Now, because this is so long, we assume, even though the magnetic field moves in a loop, it's going to move in a loop that's like this. It's going to move in a loop that's like this. Okay. So in here, it's pretty much, we assume, to be like just a straight line here. Now, there's a couple assumptions we make on a solenoid. Because all of these things are adding up, the magnetic field here is very strong. And it weakens as you get further away from these things. So one thing we can make is an Ampere loop that does this. So we know, like in here, the magnetic field just points to the right like this, okay? So I shouldn't put that on my answers, but yeah, it's going to be like that. So we want our Ampere loop to at least do that part, to do this, to match the direction of the magnetic field. But then we're going to make a rectangle. Why? Because anywhere else, the magnetic field is just going to be running perpendicular to it. So it's going to loop around like this. So, but we make a really long and far away, and we'll make a loop that looks like this. And we do that because you want either, okay, this is the important part of your loop, is you either want it to be parallel to the magnetic field or perpendicular, because if it's perpendicular, that dot product's going to be 0. So my loop is going to travel in that direction because that will allow it to be perpendicular to there. And so then we can just focus on this part here. Okay, so let's say this is a loop length, let's see, what variables do they use for everything here? This is length L. We'll call this D, with D here. Actually, did they use D for anything? No, they used A for the radius. So that distance is A. Okay, cool. So that's the Ampere loop we're going to use. Now, describe an expression for the magnetic field. Now, we're going to make a couple of assumptions here. We're going to assume that this thing is so far away, okay, like this, we'll call this L, capital L. This is so far away that this is very far, that the magnetic field very far is very weak. Like the magnetic field for this guy is pretty close to 0. Okay, the magnetic field is going to change in strength. As you get further away, it's going to weaken. So what's going to happen is you just make this loop super, super far away. Okay, so the only contribution to the loop, the line integral, is just going to be this guy right here. It's going to be literally the magnetic field times d. Okay? It's just because it's just b times the length. And that length is d. Okay? These guys, again, no contribution because they make the magnetic field makes a right angle to these components in that direction, so the dot product is 0. And then this one, we assume that we're very, very far away, so the magnetic field is 0. So this is equal to mu naught times the amount of current we've enclosed. Okay? Now, how much current did we go through? Well, the only current that's piercing this surface are the currents from these loops here, right? Like right in here, we're going to have current traversing those loops because they're moving in a circle like that. So how much current is going through there? Okay? N is the number of well, we have to think about how many turns are in here. So it's times the number of turns in here. Okay? And the number of turns, like the number in here, the number of turns or the number of wires in there is equal to, if you take the total number of turns divided by the length, this is like the density. It's like how many per length, and then times that length. Like, for example, if this was half of the coil, like if this distance were half of the entire length of the coil, then we would have half of the number of turns, right? So think of D over L as the fraction of the number of turns that are in there. So it's N over L times D. And this is L. Oh, sorry, I should use little l. That's because they said this length is lowercase l. Okay, and that's it. So the magnetic field, then the D's cancel, and you get mu naught N over L, like that. Okay, sorry, and then we have to times I. Forgot the amount, because you have that many turns, and then each of them contributes an I current to it, right? So it's like this. And this you'll recognize as if you look in your formula sheet, you have this solenoid formula. It's mu naught N times I, but this N is the density, is the number of turns per length. Okay, so they call this thing little n. So that's how you derive it from Ampere's law. Okay, let's take a look at another case here, another scenario of a magnetic field. So two plates are set up with a potential difference delta V between them. Small sphere, mass m, and charge negative E is placed in the left-hand plate, which has a negative charge. It is allowed to accelerate across the space between the plates and pass through a small opening. After passing through the small opening, the sphere enters a region where there's a uniform magnetic field directed into the page. As ignore gravitational effects, express your answers in terms of, let's put this as delta V. This should have been a delta V, M, E, B, and fundamental constants. What is the initial direction of the force on the sphere as it enters the magnetic field? So this guy's going to get accelerated. He's going to be moving to the right with a velocity V. And because he is a charged particle moving through a magnetic field, he will experience a force, right? QV cross B. Now, be careful, it's a negative charge. So we still use our right-hand rule. So my index finger's to the right, velocity. Magnetic field's into the page away from me. And so from here, my thumb is pointing up. However, because it's a negative charge, it's the opposite. So my thumb, I'll make my force going down instead. So it's going to be toward the bottom of the page here. Sketch a possible path that it will take. And so what will happen is, remember, it moves in a circle at this point. So it's going to move like this in a circular path and probably hit back down over here, a circular path. Why? Because that force is perpendicular to the velocity. So as it turns, the force is also, because cross product, the result of the cross product is perpendicular to both of those vectors. And so it's going to be a centripetal force, so it's going to move in a circular path like that. So that would be valid. You could make it wider out like this. Like those would all be valid. Like you don't know without any like numerical values or magnitudes. Derive an expression for the radius, the path taken by the sphere as it moves through the magnetic field. Okay, so here we're going to do our free body diagram, F net equals ma, and we only have one force. It's the magnetic force, and it's causing centripetal acceleration, right? So we do the A is V squared over R. So what's the magnetic field? Well, it's QV cross B. However, in terms of, so we use that to get direction, but we know the velocity and the magnetic field are already perpendicular because the velocity is moving in kind of the XY plane, and the magnetic field's kind of in the Z direction. So they're already perpendicular, so you can just multiply them directly. There's no need for an angle between them or anything like that. And so the charge is the electron, EVB, is equal to mv squared over r. One of the v's cancel. You can get r is equal to mv over eb. Now, They wanted your answer in terms of the potential. So one issue here is this velocity, we don't actually know. That's not a variable. They didn't tell us how fast it was going, but it will depend on how fast it is going. Okay, so then how do we do that? We have to now talk about this potential difference. How is it causing it to accelerate? And remember, potential difference, what it does when you move through a potential difference, you have a change in potential energy that can cause a change in kinetic energy. Okay, so Q times the change in potential is going to be the change in kinetic energy, which is 1/2 m v final squared minus 1/2 m v 0 squared. Now, there might be a sign, there might be negative. Like, you don't have to worry about the sign. Just remember that we're probably gonna lose potential energy, right? So this is like negative. So because we're technically going from lower to higher potential, so technically there should be there's a negative sign in here, which will cancel with the normal negative sign and make it positive. But I tend not to try to worry about the signs too much and just think about it. We're gonna gain kinetic energy, so we must have lost some potential energy here, and the amount lost is this. Now we start from rest, right? It's placed and it's allowed to accelerate. So if it's placed there, it has initial velocity of 0. So we can figure out this final velocity that's going. It's equal to 2e delta v over the mass of the electron and take the square root. And so now we can use that and plug that into here to figure out the radius. It's m square root 2e times the change in potential over m divided by e times the magnetic field. Okay, now if you want, you can leave it like that. If you want to simplify, because you're just like kind of picky about it like I am, you can bring everything inside. That will become m squared 2e delta v over m, and you can bring the e inside, and that will be e squared on the bottom. So you can do a little bit of canceling. And so then you get this square root of m over e 2 delta v divided by the magnetic field. So that is another way you can simplify that if you wanted to. Okay, you can also leave it like that. That's fine. All right, let's take a look at another problem. So here we have an example of where we're going to use Biot-Savart. Okay, so current travels along a long wire from the top, goes around a circular arc, and travels to the right a long distance as shown. Steady current I flows in the direction shown. Point P is located at the center of the circular arc. Assume the wire lies entirely in the plane of the page. Express all answers in terms of mu naught I, R, and physical constants. This should have just been I, R, and physical constants as appropriate. What is R? R is I didn't say the radius. R is the radius. So R is supposed to be this part here. Derive an expression for the magnetic field at point B due to the current in the wire. Okay, so here, because there's not a lot of symmetry, we can't use Ampere's law. I love Ampere's law. 80% of the time, it's like you're usable, but like in this case, because there's not a lack of symmetry, because I can't rotate this thing and it looks the same. It looks different when I rotate it. So can't really do anything about that. So we got to chop it up into little chunks. And so I'm going to break it into the circular segment here, or we'll just chop it up into little segments and then little segments here. And we just got to remember each of these segments has a DL. And then we have this segment here, chop up this segment. We have a DL over here as well. Okay, so let's talk about this first segment going down like here. The DL is like that. My R hat vector, so let's just write out Biot-Savart just to make sure we know what we're doing. It's mu naught over 4 pi DL cross R hat divided by R squared. Okay, that's the contribution. So this guy, we got to draw the R hat vector. So this guy, we're going to have an R hat vector pointing from here to that point here, right? So that's my R hat vector. It's unit length, but it points in that direction. Notice that the DL vector is parallel to the R hat, so the cross product is 0. Fantastic. That means this whole segment here doesn't contribute any magnetic field. So no contribution from this segment because of that, right? Same with this segment over here, because the R hat's going to point like this from where the segment is to where the point is of magnetic field we're interested in. Again, because it's parallel, right? The DL's to the right, R hat's to the left. Cross product, again, 0. So this guy is not going to contribute anything to the magnetic field either. So we really only have to talk about this thing. So this guy, the DL's here, the R hat's here, definitely perpendicular. But because it's a circle, the cross product, when you do the cross product, all right, what's the direction of the magnetic field? It's going to be perpendicular, so you're going to have your finger down here, your R hat's like this. This is going to be coming out of the page, so it's going to be out of the page here for this guy. And as you turn, it's still going to be out of the page. And so all we care, so we have the direction. So all the components are going to be out of the page, even if you do it down here. You do it down here, you make your right-hand rule. You draw your r hat vector. You do your DL cross it. DL down is down to the right. Sorry, let me get my finger in the camera. Down and to the right. Middle fingers up, and then again, still out of the page, right? Towards me, out of the page. So nothing to decompose, already coming out of the page. So then we only care about what the magnitude is now, which is just because they're already perpendicular, you just multiply them times the magnitude r hat. But remember, r hat's a unit length vector, so that's 1. So this will just be dl. So then our contribution is going to be mu naught. Oh, there's an I over here. Mu naught I over 4 pi dl over r squared. Now, we know the current's I. What's r squared? R squared is that distance, and it's constant the whole time because of a circle, right? This r is going to be capital R. So this is going to be mu naught I over 4 pi dl over big R squared. And so now if we want to add them all up and find the total contribution of the magnetic field, we're going to integrate, like everything is a constant, except the dl. So we're just integrating dl. And if you add up all the lengths of the dl's, what is that? It's the length of that segment of wire, which is 3/4 of a circle. Right? So this should be 3/4 times 2 pi r. Because we've gone 3/4 of the circle. Not a whole circle, right? The length is just from here to here is just 3/4 of a circle. So then the pi's will cancel, one of the r's will cancel, and you get what? 3/16 mu naught I over r, like that. Indicate the direction of the magnetic field. It will be out of the page. We just talked about that based on our cross product, our right-hand rule. And so that's that. So those are some examples of all the things that you have to do for this unit.